Welcome to ilectureonline. Here's one of those really complicated, difficult JEE type of problems that you only will find on a JEE test. I've never seen anything like this, but well, let's try to work through it and see what we get. So our 15th problem on paper 1 in the 2022 JEE Advanced test says, a small circular loop of area A and resistance R is fixed on a horizontal XY plane, and that's this little loop right there. The centered loop always on the axis of a long solenoid. So here's a long solenoid with wire around it, number of turns around it. There's current flowing in that direction. N is the direction of the solenoid, so that always goes right to the center of the loop. So we want to make sure we have that picture. The solenoid has M turns per unit length and carries current I, counterclockwise as shown. The magnetic field due to the solenoid is in the N direction. And that would make sense, because if the current goes around the solenoid, the magnetic field will be in the direction of the thumb, in the direction of the N unit vector. List 1 gives a time dependence of the direction of N in terms of a constant angular frequency omega. So the solenoid is rotating in some fashion, and that's kind of what throws you off in the beginning. But then when you look at this list, this is 4 different time-dependent equations for the normal vector, N, the vector in the direction of the solenoid as a function of time. And so either it's rotating in the YZ plane, or rotating in the XY plane, or in the XZ plane, or in the YZ plane. So there's 4 different rotations that we need to worry about, and it's the functions of sine and cosine. So at first I was a little confused. What are they saying here? But when you realize that this is simply 4 expressions or equations that give you the time dependence of the direction of N as a function of time, then it makes sense. List 2 gives the torque experienced by the circular loop at time t equals pi over 6 omega. So here is the torque experienced by the loop caused by that rotating solenoid. All right. Now, we have 4 possible options to choose from. Only one of these 4 is correct. When we pick this time dependence for N, do we get Q as an answer? Q would be minus A over 4I. That would be the magnitude and direction of the torque. If we take 2, that means if we take this expression of the time dependence of N, do we get P? P would be 0. Then we go to 3 here. If we take the third one, time dependence of N, and we throw it into the equation, do we get as a result A over 4 times J? Those are the torque results we're trying to get. So which of these 4 combinations is correct? You sit there and go, where do you start? So we need to do this very systematically. The first thing we need to realize, oh, by the way, let's see what else do we have here. They say let A equals this expression right there. So somehow we're going to get this expression, and then, of course, when we see an A in there, that A really represents what's there. So you can see this is getting a little complicated. So the first thing we need to do is find the magnetic field of the solenoid. So the magnetic field B is going to be equal to mu sub naught times M. M is the number of turns per unit length times the current I in the N direction. So that is going to be the B field. So now we need to find the flux through the loop. So the flux through the loop, magnetic flux through the loop, is going to be B times A times the cosine of the angle theta. Now the angle theta depends upon the orientation of that solenoid. So we can say, well, since it's rotating at angular frequency omega, theta will be omega times t. So this can be written as B A times the cosine of omega t. So at all points in time, that will be the flux through the loop. All right, so now we need to find the EMF induced by the rotating loop. So the EMF induced is equal to the negative d flux divided by time. So the amount of magnetic flux per unit time change through the loop is going to give you your EMF. So we take the derivative of this, And so derivatives would be, the derivative of cosine is the negative sign, so we get this is equal to the negative times the negative of the derivative of cosine gives you a positive. BA times the derivative of the cosine will give you the sine of omega t times the derivative of the angle, which is omega. So there, that gives you the EMF induced by the rotating solenoid. So now we need to find the current. And notice that this is presumably the peak current. So if we want the real current, we have to take the peak current divided by the square root of 2 to get the RMS current. And that's not clear here, but if you don't do that, you're not going to get the correct answer. So by doing this, I realized to get the correct answer, to get the correct units, I need to make sure I consider the RMS current. So IRMS is going to be the EMF divided by the resistance. And so that's going to be this divided by R, but we also have to divide by square root of 2 because this includes the peak current, not the RMS current. So that means that this is going to be BA omega sine of omega t divided by the square root of 2 times R. All right, so there's that mysterious square root of 2. And then when you multiply that times 1 over square root of 2 by one of these, that goes away. And so that's, again, I figured that out by working it out that they gave us the peak current, not the RMS current. All right, so now we have current. So now next what we need to do here is we need to find the magnetic moment. And the magnetic moment is going to be in the z direction, the k direction. And so we can say that the magnetic moment M is equal to I times the area of the loop in the k direction. And of course we have the I from here. And so that means that the magnetic moment is going to be equal to this times A, so we end up with BA squared omega times the sine of omega t divided by the square root of 2 times R in the k direction. All right, so now we're ready to find the torque. And the torque is going to be equal to the magnetic moment crossed with the B field, with the magnetic field. So now the magnetic field is equal to this. Or we could say this is equal to the magnitude of B in the n direction. So we're going to write it like that. So then when we do the cross product here, we can say that the torque therefore is equal to the magnetic moment, which is this. That would be BA squared omega sine of omega t divided by the square root of 2 times R times B, and B, well, we could simply say it's B times the direction in the n direction, so this becomes B squared, and then we're going to have K times N, K crossed, wrong one, K crossed with N, like this. So that is simply the product of the magnetic moment times the B field, and that gives us the torque, and the torque is going to be the cross product of the magnetic moment, which is this, times K, and B is going to be B times M. So I'm going to do the cross product with K times M. All right, now, at that point, what do we need to do is, because we're looking for the torque, we need to now use the value of N here given in these 4 expressions, one by one, to see what torque magnitude we're going to get. All right. So what that means is we're going to have to find the cross product of K multiplied times N, N being one of these 4. So let's start with the first one. So we're going to go K cross N. So K cross N is equal to K cross 1 over the square root of 2 times the sine of omega t in the j direction plus the cosine of omega t in the k direction. All right. So we're going to take the result of that and multiply it by this quantity right here. And then we're going to evaluate it at time equals pi over 6 omega, because that needs to be plugged in there. So when we do the cross product here, notice when I do a k cross k, that's 0, right? Whenever we do a cross product and the two vectors point in the same direction, you get a 0. And when we do a k cross j, k is in the z direction, j is in the y direction, that gives us the negative x direction. So we'll end up with a negative I by crossing k and j. So it's negative I times this quantity right here multiplied times this quantity right here. So that means that the torque is going to be equal to b squared a squared omega sine omega t times the sine of omega t, which is a sine squared of omega t. K cross n is going to be a negative I divided by the square root of 2r times the square root of 2. So square root of 2 times the square root of 2 gives us 2 times r. And then we're going to evaluate, and let me move over here, the torque when t is equal to pi over 6 omega. So that requires us to find the sine of omega t when t is pi over 6 omega. So the sine of omega times t, which is pi divided by 6 omega. The omegas cancel out. Pi over 6 is 30 degrees, which is 1/2. And so therefore, sine squared of omega t evaluated at pi over 6 omega gives us 1/2 squared, or 1/4. That gives us 1/4. So this means that the torque, therefore, is equal to b squared a squared omega times the negative, let's put it as a negative that, times I divided by 2 times 4, and you'll see in just a moment why I left the 2 there, because I need a 2 over here, times r. Okay, now you say, well, all right, that doesn't look like any of the items on list 2, but if we then replace b squared by what b is equal to, which is right here, then what we end up with is this is equal to minus b squared will give us mu sub naught squared m squared I squared a squared omega divided by 2 times 4r in the negative I direction. So this is an I direction. I already have the negative over here. And then if I look at this here, I have an a squared, a mu sub naught squared, an m squared, an I squared, omega, 2r. All I've left is minus I divided by 4r. So this is equal to minus a over 4r in the I direction. So that is my torque. I should put a vector on there. So this is my answer for the torque if I use expression number 1. And, oh, wait a minute, the r is gone. I don't have an r, like that. So minus a over 4 in the I direction. The r is already taken care of by this expression right here, by the a. And so minus a over 4 in the I direction gives me q. So if I pick 1, I have an answer q. And let's see where, I need a red pen here. So if I pick a 1, I get a q, so this is correct. And if I pick a 1, I get a q, this is correct. But I don't get the s value, I don't get the t value, so these are not correct answers. So I've narrowed it down to just 2 of the 4 possible answers. All right. Now, it's not so bad. We normally would have to do this over again. However, if we realize that if we take 2, notice that the solenoid is rotating in the xy direction. And if the solenoid is rotating in the xy direction, there is 0 flux going through the loop because the normal to the loop is in the z direction. So if we take 2, we have 0 flux, therefore 0 torque. So 2 should correspond to P. So which of these 2 gives us a P? Oh, bummer. There we are. 2 gives us a P, and 2 gives us a P. Oh, that doesn't help us. It's still either A or C. They want us to do 1 more of these. Can you imagine? They only give you 3 minutes to do this whole problem, and now we have to do this again. So have to pick a third one probably. Let's see here, which one should I pick? I can pick, let me pick this one here, 3. So when I pick 3, oh no, I don't want to pick 3 because 3 gives me S in both cases, so that's not the one I want to pick. I want to pick number 4, which is differentiated. I will get either T or R for the correct answer. All right, so now I need some board space. We're going to go and use expression number 4. And I started working on that, and then I realized, wait a minute, I have to be careful here because now we have a different expression for the rotation of, or the position of n as a function of time. Notice that in the z direction, we end up with a cosine of omega t when we chose 1, as we did for 2 and 3, but for 4, in the z direction, we have a sine of omega t for the magnetic flux. So therefore, when we try to find the magnetic flux through the loop right there, we can only consider the k direction, which gives us a sine of omega t. So therefore, we can say that the magnetic flux through the loop is equal to, is equal to A times B times the sine of omega t. And of course, B is going to be equal to that, so we could write it as A times mu sub naught mi times the sine of omega t. And then realizing that we use the peak value for I here, we really want the IMS value for I because we want the RMS flux. That means that I sub B is therefore equal to A times B times the sine of omega t divided by the square root of 2. All right. So now when we want to find the EMF induced is equal to the negative change in the flux divided by time, which is equal to the derivative of this with respect to time. And so we end up with the derivative of sine is the cosine times the derivative of the angle is omega. So we end up with a positive times the negative, which is a negative AB omega times the cosine of omega t, all divided by the square root of 2. And so that's the magnetic flux through the loop when we use this rotation and that expression for the normal of the magnetic field from the solenoid. So the next thing we want to do is we want to find the current induced, which is, the current induced, which is equal to the EMF divided by the resistance. And so that's going to be minus AB omega cosine of omega t divided by 2, the square root of 2 times R. All right, so now the next thing we want to do is find the magnetic moment, which is the current times the cross-sectional area of the loop in the k direction. So there's the current, we multiply times I, so we end up with an I squared, so the magnetic moment is equal to minus A squared, this A times that A gives us A squared, times B times omega times a cosine of omega t, all divided by the square root of 2 times R. All right, the next thing we want to do is we want to find the torque. And the torque can be found by taking, wait a minute, I'm forgetting my k unit vector. So the next thing we want to do is then say that is equal to magnetic moment times the B field. And so that the torque is therefore equal to the magnitude of that, which is minus A squared B omega times a cosine of omega t divided by the square root of 2 times R times the B field, so that makes us B squared, and then we have the direction of M, which is K cross with the direction of the B field, which is N. There we go. So now we have to do a cross multiplication of K times N, and now we're going to use N of the fourth expression. So that means that K cross N is equal to K cross 1 over the square root of 2 times cosine of omega t in the j direction plus the sine of omega t in the k direction. Of course, when we do a cross product, when we have k cross k, that gives us 0. So this goes to 0. And k cross j, we have k cross j gives us a negative I direction. And so that means that this is equal to negative 1 over the square root of 2 times the cosine of omega t in the negative I direction. And that's the product, cross product of k cross n. From here, we multiply that times this. And so, there we get the torque is equal to minus a squared b squared omega times cosine omega t times cosine omega t gives us cosine square of omega t divided by square root of 2 times the square root of 2 gives us 2 times r in the I direction. And now all we have left to do is find the value for cosine of omega t when t equals pi over 6 omega. So cosine, move a little bit here, cosine of omega times t, which is pi over 6 omega. And we have to square that. Omegas cancel out. Pi over 6 is 30 degrees, which is the square root of 3 over 2. So we get the square root of 3 over 2 quantity squared. So that means that this is equal to 3 over 4. So instead of writing cosine square of omega t, we write 3 over 4. And so we have the torque is equal to minus a squared b squared. Now remember that b is equal to mu mi. That gives us mu sub naught squared m squared I squared. We have the omega. The cosine square of omega t is 3 over 4 times 2r in the I direction. Now remember that a is equal to this expression right here that takes care of the a square, mu sub naught square, m square, I square, omega divided by 2r, and we're left with, I think I'm messed up the negative sign. Let me check real quick. So we have derivative sign is a cosine, so that gives us negative. But I have a negative times a negative. This is where I went wrong. So this gives me a negative, and this is a negative. Negative times negative gives me a positive. There we go. We end up with a positive torque. Here we are. And so finally we get a torque is equal to A times 3 over 4 in the I direction. And now, which of these answers corresponds to this? We have an A, a 3 of 4i, that corresponds to R. And so, the only possible answer we have is this one right here. That means that C is correct and A is not. That was a crazy problem. And it certainly takes a whole lot longer than 3 minutes to solve this. But that's what makes the JEE Advanced tests so difficult, is that it takes sometimes a long time to figure this out, unless you can find a shortcut method to work through this. But I wanted to show you the development of how you get to the answer, because you need to know the process, you need to know how to calculate the magnetic field of the solenoid, how to find the flux through the loop. The flux through the loop is going to depend upon which rotation you're going to use in the k direction. So notice that here you have a k direction, so we have flux based on cosine of omega t. Here you don't have a k direction, so there's no flux through the loop. Again, use a cosine of omega t, use a sine of omega t for the fourth one, which is what we did here. Then you find the EMF by taking the time derivative of the flux. Then you find the current by taking the EMF divided by the resistance. Then you find the magnetic moment, which is the current times the cross-sectional area of the loop in the k direction. Then you find the torque by taking the cross product of the magnetic moment and the magnetic field. And then you have to then cross the k direction of the magnetic moment with the n direction of the magnetic field, based upon which of these four that you pick. And then once you pick that, you get an expression for the torque. Notice that A is equal to all these constants right there. And then once you make a replacement, you can find which of the items on list 2 corresponds to that. And in this case, we had to do it twice. We had to do it for the first expression, for the fourth expression, and realizing that the second expression we get is 0 for the answer. And that is how it's done.